And now times dx, but what's dx?
3 cosine theta d.
3 cosine theta d theta. Right? Now, look, would you agree that this integral just got kind of better because now we have trig stuff in there and we can kind of handle trig stuff? But the thing is, we've switched from x to theta now, right? So whatever we get as an answer here, we're going to have to go back to x at some point. Okay? We have to. But at least this seems doable now. Any other questions before we proceed? So,
You get, would be,
let's take your constants out. Take your constants out.
3, the integral.
Let's do them both. 9 integral, right? So we'll do 3 times 3. We'll just take it out. And then
Theta, d theta. And then
we had 2 cosines. We had this one and this one. Right. Okay, so squared. All right. So from last class, how do we handle cosine to an even power?
take out a cosine. Wait, no, that's 1/2, sir?
Yep, that's it. So we're going to take this and we're going to replace cosine squared with 1/2 1 plus cosine of 2 times whatever the argument is. So for us, it's 2 times theta, right? 2 theta d theta. Because this is x for us. So the formula says it should turn into 1/2 times 1 plus cosine 2x. So for us, it's going to turn into 1/2 times 1 plus cosine 2 theta. Is everyone on board with that?
So then we put a constant.
Yeah, we can pull the half out. 9/2 integral, we'll just have 1 plus cosine 2 theta d theta. Herman? Going all right? Okay. Can we take the antiderivative of this now?
Yeah, we could,
Okay, so what's the antiderivative of 1?
theta.
Theta, good. And then this one, I'll start writing it as you tell me here. I have 9/2 out front, and then you said theta, and then plus antiderivative cosine 2 theta.
Should be sine.
Missing something out front.
1/2.
1/2, good. 1/2. 1/2 sine 2 theta, right? That's the antiderivative cosine 2 theta. And that's it, right? That's it?
Plus c.
Plus c, yeah. Plus c. There it is. There's our antiderivative. But it's not in terms of x. So when we're saying, hey, what's the antiderivative of this function, we want to know what is the antiderivative in terms of x, right? Our answer is in terms of theta. So I guess it's like, I don't know. Y'all understand we're not there because this needs to be in terms of x?
Well, x equals 3 sine theta.
We do have a relationship, don't we? Yes.
yeah.
So we need to go back now, and we need to somehow find the connection we had between x and theta. And as Scott just mentioned, we did have a connection. The connection we had, we actually created it. It was this connection, right? And way back in the beginning of class, we did a problem where I said these skills are going to be needed later. And we drew what was called a reference triangle. Do you remember doing that in here? It's been like 3 weeks, about. So we start with this right here. What I'm going to do from this is I'm going to isolate sine theta by dividing both sides by 3. Okay? Y'all agree with that? Y'all understand where this came from? This was our substitution that we made in the very beginning. I'm going to isolate sine theta, and then I'm going to draw a right triangle. And using this information right here, I'm going to call the angle here theta. And we know that sine of an angle is the opposite over the hypotenuse, which means that I can label this side x and this side 3. And if we have 2 sides of the right triangle, we can always solve for the third one. So this side you can solve for, and I'm trusting you can solve for it, will be the square root of 9 minus x squared. Oh, we've seen this before, haven't we?
Yes.
Yeah, that's actually that, isn't it?
Yes.
Okay, now, This was all just so we could get a real good idea of our relationship between x and theta, right? We have a bunch of relationships here between x and theta. Yeah? Okay, let's go back up to the answer. I need to first see if I can turn theta into something with x in it. How about right here? How can I get theta by itself? Take arc sine on both sides, right? So if I take arc sine of the left side and arc sine of the right side, I have an expression for theta, don't I? And that expression for theta is in terms of x. So I'm going to replace theta with arc sine of x over 3. Now what about this? This is the problem piece right here. The problem is that this is saying we need to know what sine of 2 theta is, right? We know what sine of theta is, not 2 theta. And you are not allowed to just like stick a 2 in here or multiply a 2 and distribute it through. Those aren't the same thing. We have to first use the double angle identity to make this turn into what?
Into 2
Yep.
sine.
So this turns into
2 sine x.
2 sine theta, right? Because it's theta. Cosine theta. Pre-cal. Now the benefit of this is that now this expression is equivalent to this expression, but it has sine theta, which we know, and it has cosine theta, which we know here, adjacent over hypotenuse, right? Cosine is adjacent over hypotenuse. We know every trig function for theta from this triangle, don't we? We know sine of theta, we know cosine of theta, we know tangent of theta. We know every trig function we could ever need is off this triangle, right? So I think I'm ready. Here's where we are. We are at 9/2 parentheses theta, which we said was arc sine of x over 3, right? Plus, now I didn't do this a second ago, but this half and this 2 are gone, aren't they? Like that 2 is really up there and half of that's gone. Sine of theta, which is x over 3, so sine of theta right there is my x over 3, and then times cosine theta, which is adjacent over hypotenuse? Adjacent over hypotenuse? So square root of 9 minus x squared over 3 plus c. There it is. I can do a little bit more cleaning up. I think I'm going to do just a little bit more cleaning up. But I mean, that right there is the antiderivative in terms of x. So to clean it up, I'm going to distribute the 9/2 through. Okay, when I put these 3's together, I get a 9, don't I? But then when I come through with the 9/2, the 9's cancel, and I should just be left with a 1/2 in front, right? Because this 2 didn't go anywhere. Just came in. And then x root 9 minus x squared plus c.
Like, hypothetically speaking, what would be an application for this type of?
That's a great question.
Because I'm trying to see what would it be used for.
Okay, so you're asking a very good question, all right, which is, you know, what would this be used for? Where's the application? I'm going to be honest with you. I think no matter what you do in the future, unless you're up here trying to teach this to somebody, right, you're never going to have to do an integral using, what is this, trig sub? Not going to happen. If you ever need to do this integral, you can go to a computer and have it do it for you, right? Now, that sucks then. Why are we doing it, right? Would you all agree that this is a level of thinking and a level of processing of information that goes beyond anything you've ever done mathematically before? Yes? No? No? I mean, is this a level of problem solving that kind of makes even the calculus look a little bit trivial? Yeah?
It's like using computers like a 3D printer, but first you must know how to build a 3D printer in the first place.
Yeah, I mean, you could say, like, that was another answer I could have given, which would be, look, we do have math majors in here. Like, I know we do. And math majors we have to always hang on to the people who understand the mechanical of how to do it, right? Otherwise, you don't know the coders that are writing the programs for Wolfram Alpha. You know, how do we know whether or not those are actually giving you correct answers? Like, someone always needs to maintain the integrity of the subject. And if you remember, like, this is a math class, right? This is not an engineering class. This is not a computer science class. So really, this should be about purely the mathematics. And in that case, you know, application, well, you're not going to do this. But so I'm trying to give you the answer I personally think is the most important, and that is, this is about critical thinking, and it's about problem solving. And if you can do this sort of problem solving, then as you move on and become whatever engineer, whatever it is you want to do, your bar for what you thought you could do just keeps getting higher, right? So this is, I think this is where most people's math bar goes pretty high up. You can see how many people can go over it, right? Is that sufficient?
Yes, sir.
Okay. Because I don't want to lie to anyone and be like, oh yeah, you'll be doing this you'll be doing this, and I mean, you will do it. I mean, you still have to get through, probably most of you have to do some sort of engineering analysis course. I mean, this stuff you're going to be doing this stuff by hand for a long time. But at the end of the whole degree program, what is it that you want? What is the company looking for? A frickin' problem solver. They're looking for someone who's going to solve problems, right? And the fact that you've gone through all these courses demonstrates that you have that ability. That's my view on it. Okay. Yeah. All right. We're done. Yes. Yeah. That's the antiderivative. Maybe we should check it. Let's check it. Let's check it. Come on. It's not that bad. Let's take the derivative of this. All right, so here we go. I'm going to go fast. Okay, 9/2 times this, 9/2 comes for the ride. I'm just checking here. 9/2 comes for the ride. The derivative of arc sine of something, 1 over the square root of 1 minus the something here squared, x squared over 9, right? Chain rule, times the derivative of what's inside, 1/3. Okay, that's the derivative of the first term. Yeah? Plus, okay, here I'm going to do a product rule right there. So I'm going to do derivative of 1/2 x, which is 1/2, times the second one, right? Plus the derivative of this. So what's the derivative of the square root of something? 1 over, yeah. Right? Times the derivative of what's in here,
which is negative 2x.
times the first function. Right? That's it. Maybe we messed up. Okay, those are gone, right? Yeah, I think that's good. Let's clean it up. What does this need to turn into at the very end? Square root of 9 minus x squared. Okay. So let me do a little more here. This and this becomes a 3, right?
So that becomes 3/2.
3. I'm going to do it a little different because I'm about to get a common denominator and put all these together. Okay, here we go. Plus root 9 minus x squared over 2, and then plus, minus. What about this minus though? Right, so minus, on top we have x squared. On bottom we have 2 root, what, 9 minus x squared? Okay, I see, I'm going to try and get a common denominator of 2 root 9 minus x squared, right? Okay, I'm going to try and do that. The problem is this one isn't quite that, is it? Yeah, so let's do this. If I rewrite that, I can write it as 9 minus x squared over 9. Do y'all agree that that's what this is?
Yes.
And then I can pull the 9 out of the root as a 1/3. Like the bottom can come out like that. Yeah? So imagine on the bottom of this, since I'm checking, I'm just going to erase and cheat here. So what came out of this root?
1/3.
a 1/3, right? And when I do 1/3 here, it comes up and really turns this into a 9. Because the 1/3 flips up, right? Okay? Now, let's get a common denominator. Here it is. This, all I'm missing here is what? That root. So root 9 minus x squared, root 9 minus x squared. I can put them all together. 2 root 9 minus x squared. So I have 9 plus this right here. They multiplied, right? So the root went away.
So it's 81.
9 minus
Yeah, minus
x squared. And then this one right here,
minus x squared.
minus x squared. That doesn't look right. Yeah, but that's right. 18 minus 2x squared over 2 root. Oh, yeah, no, I see it. Never mind. It's right. I have to rationalize it. Okay, so let's divide everything by 2. 9. Got it? So we have 9 minus what on top? X squared over square root of 9 minus x squared. Right. I like to look at it this way. This one is really the root squared, isn't it? So this is like the root squared, and this is just the root, so one of them cancels, and you're left with just the root on top. However you do it, we're there. Right? Do y'all agree we're there? Okay. So it worked. Yeah, this is, so we've just started this, all right, trig sub, that was our first example, and this is how we deal with square root of 9 minus x squared, right? This is kind of a summary of what I showed you a second ago. But remember there was 2 others? So what happens if you see the other way around, square root of x squared minus a squared? So if we flip them over, your trigonometric substitution is not a sine theta anymore. It's actually a secant theta. And then that big ugly square root thing turns into a tangent theta. And the derivative of that turns into a secant theta tangent theta d theta. So that means you're going to convert this thing into stuff that has tangents and secants, which is why we talked about how you deal with tangents and secants. And then there's the other one where you have square root and there's a there's square root and then there's a sum between the two. In that case, our trig sub is a tan theta, and then we have the root thing turns into this, and the derivative is that. So we still have to talk about 2 other ways, and we have to do some more examples. And we still have 10 minutes, so we're not quitting yet. I would like to do one more here. Let's, do I want that one? Let's do this one. Is there anyone in here who is pre-med? Yeah? But it's not required for pre-med, right? Cal 2?
No, I got to do Cal 2 for the environmental engineering.
Yeah, some medical schools are requiring Cal 2 now.
UT just started
Yeah.
Cal 3.
Oh, really? Cal 3?
UT Austin.
Yeah, so getting back to your question, Hogan, right? Like, I'm pretty sure no doctors need to do trigonometric substitution. So why would they make Cal 2 a requirement? To weed them out, right? To weed them out. To weed out There's too many people want to be doctors. We just keep upping the math requirement, and that'll weed the herd out, right? You can kind of look at that in terms of engineering computer science too. Like, you only want the students who can handle like a higher level of thinking in these courses. If your bar was real low, then you just have too many people. You know, I don't know. There's a lot of reasons why we have to do this, but. All right. Well, does that look like trig sub to you? Well, do you see a square root of a squared and x squared somehow together there?
Yes, sir.
Yes,
Yeah?
sir.
Okay, so I'm seeing something that looks like this. A squared plus x squared. Y'all seen that? Okay, what would a be here for us?
3.
A is 3 again, right? It's not always 3. Now, what is the trig sub that we do? So I'm going to go to my little formulas. And if we see, there it is. I have to leave it up top here so you can see it. If we see square root of a squared plus x squared, then we're going to make a substitution. X is equal to tan theta. So here's my trig sub. X is equal to a tan theta. But a for us was what?
3.
3. So we are going to make this substitution. 3 tan theta. Now, according to that, what do we know? This big, ugly x squared plus 9 thing, what do we know it's going to turn into according to this little box?
3 secant theta.
3 secant theta. Okay, so that's just 3 secant theta. And we could prove it by actually replacing that with 3 tan theta and then going through factoring out a 9 and doing Pythagorean identity, but this is just shorter if we just go off of that. Now, what does dx become?
It becomes 3 secant squared theta.
Yep, right here. It becomes a secant squared theta d theta, so we know that this is going to become 3 secant squared theta d theta. Are you kind of catching on to how the actual choice is made here of what we do? Okay, now we rewrite the integral. Let's see. Oh, by the way, G, the guy G, he has the flu. So if you start feeling bad, then that might be what's happening. James Sykes is up. All right, James, help me rewrite this integral, please.
We are going to be rewriting it as 1 over, the way I wrote it was parentheses 9 tangent squared,
Theta, good.
and then multiply that by 3 secant theta.
What do y'all think of that so far? That's x squared, right? This is x squared. That's this right here, squared. And then you have the root part here. Were you done?
At the very end, dx.
dx. So what is dx going to be written as?
Dx is going to be rewritten as 3 secant squared theta d theta.
Good. Don't forget the dx. I didn't think you did, James, but that happens a lot on tests. People forget the dx, and they just, for some reason, write d theta here. That dx gets replaced with all of this crap right here, right? Now, remember, the dx is kind of like on top, and then this stuff is on the bottom, right, for this problem? So do you see we can start algebraically, like, cleaning things up? Like, we can kill off these 3's. One of these secant thetas is gone. So this secant theta is gone, that one's gone. And this 9 right here can actually come out as a 1/9. So what's still on top? Secant theta. D theta is out there also. What's on the bottom? Tangent squared theta. So that's where we are. Now, unfortunately, this does not look like the format that we had before, like earlier in class, because we got tangents on the bottom instead of both secant and tangent on the top. So does anyone recall what I did on these problems when we really didn't have like a direct way to go with that shortcut? I recommend that you turn it into sine and cosine. So let's go and write 1/9 integral secant is 1 over cosine theta. And then tangent squared would be sine squared theta over cosine squared theta, d theta. So I'm just rewriting secant theta and then over tangent squared theta. And then I'm going to flip, right? I'm going to flip.
Multiply by the reciprocal.
Multiply by the reciprocal. So I'm going to bring the cosine squared theta here,
And the
sine squared theta there, right? So,
cosine simplifies out.
so yeah, the cosines, I still have the 1/9. So what am I left with?
You're left with
Cosine theta on top, right?
cosine theta on top over sine squared theta.
D theta, right? You could do cosecant times cotangent. Deb? Do you see anything on how to do this, Deb? Every time you get a new integral, you kind of want to hit the reset button in your mind and just kind of start from the beginning, like what could you try here? We're about to be out of time, Deb. Hurry up, Deb. We're running out of time, Deb. Hurry. No, I'm kidding. Basic U sub. Do you see a basic U sub? Sine. U is sine. Look, U is sine theta. Du is what? Cosine theta d theta. Right? There's U squared on the bottom. Cosine theta d theta right there. So this is really just going to turn into 1/9 integral 1 over U squared du. Basic U sub. Not yet, we need the antiderivative, right? I'm out of time. The antiderivative of that should turn out to be negative 1/9 U to the negative 1 plus a constant. I'll trust that you could do that with the power rule. And now I have to replace U with what? Sine theta, and then sine theta with something with x.
Oh, you have to replace
I got to go
theta
back
with
and,
x.
yeah, I got to go figure it out later, and I'm out of time.
So you have
That's-
to replace your thetas with x, right?
Yeah.
And put
So
it
somewhere I'm
with
probably
x.
have to draw a triangle because our information about theta came from a substitution we did that x was equal to 3 tan theta, I believe, right? No. Was it 3 tan theta?
Yes.
That was our substitution? So we need to go draw a triangle off of this so that we can figure out what sine theta is.
Right.
Yeah, but we'll do that next class.
And we divide by 3. That
By
means
3?
x over 3. We
Yep.
use our reference triangle.
Yep.
And we know that tangent is adjacent over opposite.
Right there.
Got
Yep.
it.
Yep. So now you can tell me just by this what sine theta.
What sine? Sine is opposite over hypotenuse, so it would be x over 9, the square root
Yep.
of 9 plus x squared.
Yep. So what? Or what? Oh, because it's 1 over. Yeah. So we still have to. We have to still. Yeah. We're out of time. I'm not going to keep you longer. I didn't even talk about the test. Shit, why didn't y'all stop me? Okay. Everyone's like, maybe we shouldn't do a test. No. Okay, I'm about to look at my fall 2019 test. The fall 2019 test was 13 questions. 13. Out of the 13 questions, the first 5 had to do with the sections on like arc sine, like the inverse trig functions and stuff, where you had to like take the derivatives using chain rule for those, arc cosine and hyperbolics and all that. And then at number 6, we start picking up with antiderivatives. And it's just integral signs. I mean, that's the rest of the test, just here's the integral, figure it out, here's the integral, figure it out. So in that, you definitely have to demonstrate power rule, right? You got to know the power rule. You got to know basic U sub, right? Basic U sub. You need to know how to use U sub when it's not even that apparent that it should be U sub. So like I did a few problems where I was like, we're going to do U sub here, even though it doesn't look like U sub's going to work, right? So maybe go back and look at that in the notes. And then integration by parts. Looks like there was about 3 problems, integration by parts. So, yeah. You need to be able to do integration by parts repeated, right? So you might have to do it more than once within the same problem. U sub, I didn't on this test, but you know, anything I've done in class I think is fair game, anything that's in the homework. So I think the most important thing for you, I mean, and you probably gathered this from taking quizzes, is that you need to practice at home being in a testing environment. So what I think, you know, what I always like to recommend is have a friend or family member or whatever, girlfriend, boyfriend, whatever you're interested in, you have them go pick a few problems for you randomly. And then put them down, start the clock, and just use your formula sheets and see how you do. If you can do them, you know, go from your homework problems. And if you can do them in a decent amount of time and you don't have to go refer to your notes, then that shows you're kind of ready. Because if you're looking at the problem, spending 10 minutes going, what method am I going to use here, that's going to really slow you down. So you just have to keep practicing till you get comfortable. Other than that, I will stick to it being very similar to homework and quizzes. And my quizzes, like, you've seen them, right? You've done them. So, you know, I'm not going to, this is your opportunity to get a good grade. Like, this test is the one you want to start out with a good grade. You don't want to start out low because it gets, I think the tests are harder from here. Yeah. Okay, have a good weekend.
Sections we should keep looking over, or?
Well, I would invest a lot of time in the integration, right?
Okay.
So I mean so starting from when we were doing substitution, I mean not power rule,
Okay.
right? Then U sub, integration by parts. Those are the 3 main things on there.
Okay.
Yeah. But make sure you go back and look at those first sections where we talked about like the hyperbolic and the inverse trig. Make sure you know their derivatives, but they're all in your formula sheets. So it's not like you're going to be stuck without it.
Do you have office hours tomorrow? I know.
What's tomorrow? Friday? I'll be in my office tomorrow. What time are you
Well,
looking?
I work from 9 to 2, so anywhere between that time.
In that time?
Yeah, from 9 to 2.
Yeah, I mean, I should be there in the morning, and you should probably be here